So welcome everyone to this week's seminar. So today's speaker is Chandan Hati, who is at the moment at a technical university in Munich. Chandan did his PhD in Ahmedabad at the PRL under the supervision of Utpal Sarkar, and then went on for a postdoc in France at Clermont-Ferrand University. And now since 2019, he is in Munich at the TUM, and he will be moving to Brussels. So Chandan has been working a lot on neutrino physics and also all other topics in beyond standard model physics, but specifically today he will tell us about low energy probes for Dirac versus Majorana neutrinos, so beyond neutrinoless double beta decay. So please, Chandan.
Yeah, thanks a lot. So I think first of all I should thank you for inviting me to give this seminar, and a very warm welcome to everyone who could join us. So today I'm going to talk about mainly the low energy probes for the nature of neutrinos, mainly going beyond the standard neutrinoless double beta decay. And the bulk of the talk will be based on these three works. One of them is still to appear. So to give an outline of my talk, I'll start with an introduction to neutrino masses, and then how they can give us direction in beyond standard model physics search. Then I'll try to motivate how the lepton number violating interactions can be used to actually probe the beyond standard model physics. In particular, I'll try to shortly highlight two popular approaches, namely the effective field theory versus the simplified sterile neutrino framework. And then with a short motivation of why one should look beyond the neutrinoless double beta decay, I'll try to mainly cover two topics. One is lepton number violating meson and tau decays, and another exotic possibility which we recently worked on, which is trying to probe Dirac versus Majorana nature of neutrinos at 7 experiments. Okay, so the neutrino oscillations are currently the only laboratory evidence of BSM physics. And what it tells us is that in standard model, essentially we expect purely massless neutrinos, as well as the lepton number and flavors are totally conserved. The only observable that one can think of potentially is the leptonic EDMs, but they're also induced at 4-loop level and they're extremely suppressed. So there is practically no hope of seeing anything. But what it essentially means is that if we see any of the signals for lepton number violation or flavor violation or something like EDM, then that would essentially be a clear signature for the beyond standard model physics. Now, the charged lepton sector also hosts a number of tensions with respect to standard model, namely the famous G-2 mu, which has been lingering around for a while. Then recently, the G-2 electron also seemed to get some kind of a discrepancy with respect to standard model. Then there is the B decay anomalies in charge and neutral current modes. The 17 MeV anomaly in beryllium nuclear transitions, and so on. But theoretically, there are some other strong motivations to go beyond the standard model. Some of them are the observed baryon asymmetry of the universe. Then there is dark matter, dark energy, and so on. Finally, there are also a number of theoretical caveats which also motivates physics beyond standard model, such as hierarchy problem, gauge coupling unification, incorporation of gravity, the maximal parity violation that we observe in standard model, and the list goes on. So what essentially do we expect from a mechanism of neutrino mass generation? Well, I mean, it should explain the neutrino oscillation data that we have been collecting since a while. It can potentially also address some of the shortcomings of standard models, such as the baryon asymmetry of the universe, dark matter, etc. It can potentially improve some of the theoretical caveats that I mentioned, or at least not worsen them. So keeping them in mind, in general, there are two possibilities for neutrino masses. One is the standard Dirac mass, where, like all other fermions, one essentially adds a right-handed counterpart to the neutrinos and just writes a Euclid coupling. And that essentially gives the Dirac mass. But the problem with such a mass term is that one needs a Euclid coupling which is extremely tiny, which some people consider as fine-tuning. But the main negative part of having such a scenario is that it will be extremely hard to test such a scenario, because even though it can give something like charged lepton flavor violation or EDMs, but they're still extremely tiny to be probed in any time in future. The more interesting possibility, on the other hand, is the Majorana mass, which only requires left-handed neutrinos. But the neutrino is its own antiparticle in such a scenario. And the smoking gun signal for such a mass term can be lepton number violation. Of course, that means that there are a number of lepton number violating observables which can potentially probe such a scenario. The standard seesaw mechanism would be an example of such a mass mechanism. So there are numerous possibilities of realizing this Dirac and Majorana neutrino masses. For example, we have the famous 3 types of seesaw. Then there are low-scale seesaws like inverse seesaw, linear seesaw, and so on. There are radiative models at 1, 2, 3, and so on loops. There's left-right symmetric model where one kind of makes the right-handed sector symmetric to the left-handed. And I mean, the list just goes on. So of course, the neutrino mass has been a gold mine for the model builders. And oftentimes such models come with additional benefits, which addresses some of the shortcomings. But the problem is that there are too many possibilities spread across a huge energy scale regime. And oftentimes each of the models would invoke new physics, which has very distinct signatures at direct searches. So it's rather hard to test all of the models separately, but one can roughly classify the neutrino mass models into 2 categories. One is the high scale scenario, which is roughly around the gut scale. In such a scenario, of course, one has order 1 Euclid coupling, which is much more natural. One can have high scale vanilla leptogenesis. However, such a scenario is extremely hard to test, with one of the recent windows being the gravitational waves, which can potentially access such energy scales. On the other hand, phenomenologically, much more interesting case would be the low scale mechanisms, which can range anywhere between kiloelectron volts to 100 of TeV. In such a case, of course, one needs some kind of a symmetry or loop suppression to account for the smallness of the neutrino masses. And leptogenesis can be realized using resonant or oscillation mechanisms. The interesting part is that these kind of scenarios usually predict new physics within the reach of current or future experiments. So with all of this in mind, how do we proceed about probing such scenarios? One of the popular approach is to use the effective field theory, so to say. So in such a scenario, one basically integrates out all the heavy new physics and essentially matches them to operators which are invariant under standard model gauge group and only involves light standard model fields as the outer legs. And all the effects of the heavy new physics are essentially dumped into the Wilson coefficients, which are just a scalar number. And depending on whether we want to look over the standard model symmetry breaking, for example, at the LHC, this can be a good choice. But if we want to look into observables which are at rather low scale, then one can further match this standard model effective field theory operators to the broken phase operators, which only respects the broken standard model gauge group. And one can essentially use this effective field theory up to the running effects to kind of constrain the new physics. The good part about such an approach is that it's extremely robust and model independent, so it applies uniformly across all models. But the bad part is that it can often break down. For example, if one has light new physics, for example, if there are additional light neutrinos. So there are some remedies, like one can do the new SMEFT, where one explicitly includes right-handed neutrinos also into the light fields, or other variants of the standard model effective field theory. The other problem is that the exclusive signatures to a particular new physics scenario is, of course, missed in such an approach. For example, a resonant production of a new physics field in LHC cannot be accounted for in such an approach. So the essential idea, in terms of at least, if one talks about the standard model effective field theory, then the lepton number violating operators only appear at odd dimensions, starting from the dimension 5 Weinberg operator. And then one can go higher dimension and then try to probe them using different observables by matching them to low energy or high energy observables as needed. The other approach is so-called the sterile neutrinos. By sterile, it is implied that such fields are neutral under the standard model gauge group. However, they can interact through mostly active sterile mixing. I mean, there are exceptions, and we'll see one of them in sevens. So in such an approach, the mass eigenstates are more than 3. And consequently, the PMNS mixing matrix should be extended, and the whole extended PMNS mixing matrix should be unitary. That means that the block that we call the standard model PMNS is no longer necessarily unitary. So the positive thing about this approach is that this scenario can roughly account for all the different seesaw type of scenarios, which becomes apparent if one looks into this Lagrangian. So the lambda term is essentially nothing but a Dirac kind of mass term between the sterile neutrino and the active neutrino. And then one can also add a Majorana mass term for the sterile neutrino. And depending on whether the Majorana mass term is much, much larger than the Dirac mass term or smaller, one basically recovers the different seesaw limits. Okay, so now with these two approaches in mind, we move to the lepton number violating observables. And undoubtedly, the neutronless double beta decay is one of the best probes of lepton number violation, and for a good reason, because if one observes a double beta decay, then that necessarily implies that light neutrinos are Majorana. And the rate of such a process essentially depends on some phase factors, which comes from atomic physics, which is the G here in the half-life. Then there is nuclear matrix elements, which are the main sources of uncertainties for the double beta decay at the moment. And then there is the new physics part, which is contained in what is called the effective mass, which is nothing but the mixing elements squared multiplied with the mass eigenstate. So the current best limit comes from Camlin-Zen, which I think they updated the latest limit in 2022 only. And if one, depending on the different nuclear matrix elements, they're already probing the inverted ordering. There are also other possibilities, such as emission of Majorana, which is some kind of a light bosonic particle, which can carry the lepton number. or there can be exotic double neutrino, double beta decay. So depending on the distributions of this kind of exotic modes, one can actually also probe some of the new physics scenarios. But the limitation of neutronless double beta decay or the associated modes is that they're only sensitive to the first generation of charged leptons. And there is no reason why the first generation charged leptons should carry sufficiently large lepton number violation. It might happen that it occurs in the second or third flavors. Therefore, it's important to look into the other flavors as well. So first, of course, the LHC or the future colliders would be one of the possibilities to look for rather heavy lepton number violation scales. For example, the dimension 5 operator in SMEFT has already been simulated, and the latest experimental measurement from CMS is already probing order 10 TeV kind of mass scales of lepton number violation. For dimension 7, it's slightly weaker. It's around 2 TeV or so. And for dimension 9 and above, of course, I mean, there is no dedicated analysis yet. So there's a lot to be done. However, as I said, that the EFT approach cannot really capture the resonant effects. So oftentimes it's also important to look into more simplified model type of constructions, which can, of course, account for the resonant production and can give significantly tighter limits. In terms of low energy probes, one has the charged lepton flavor and number violating observables, such as a charged meson decaying into another charged meson and same sign dilepton, or tau decaying into two light mesons and a different flavor of lepton. On the other hand, one also has neutral meson to neutral meson kind of decay with two neutrinos, and these kind of processes are essentially flavor universal in the sense that the neutrinos can be of any flavor because we can't really detect them. So they give a very coherent constraint across the different flavors. There's also mu to E lepton number violating conversion, which is, of course, it has a huge physics potential, but the problem is the nuclear matrix elements, again, are not super well computed. So currently the bounds are relatively weak. And then there are, of course, other possibilities such as the neutrino fermion scattering. One of them can be sevens, or something like non-standard interaction lepton number violation in long baseline neutron oscillation experiments. So just to give an example, in case of dimension 7 operators, which of course doesn't have any resonant mode, so we just assume that it's SMEFT dimension 7 operators. And we kind of looked into all the different operators and compared double beta decay with respect to the second and the third generation observables in LNV. And in some cases, the mesonic observables can be quite comparable, I mean, and even better than the LHC. And there are even operators which doesn't really involve quarks, so cannot be really constrained by the double beta decay. Such operators can also be constrained by exotic muon decay or this kind of low energy observables. Okay, so then the first case that I want to discuss in a bit detail is the semi-leptonic meson or tau decays. So there are several experiments which already collected data on this lepton number violating meson decay modes. However, the BEL2 is supposed to really improve on the tau decays as well as some of the heavy meson decays. And then Na62 is supposed to improve on the kaon decays, which seems to give the most tight constraint on the different new physics scenarios. So essentially, if the sterile neutrino is sufficiently light, then it can be produced on shell in the meson decay. And such kind of decay process then can be resonantly enhanced. But the important part is that depending on whether the sterile state is Dirac or Majorana, one actually picks up different kind of dependencies in the amplitude. And this essentially boils down to the fact that if there is only one sterile neutrino, then the Majorana phases, which should come in the mixing elements of the active to sterile transitions, those things cancel out, and one has similar rates for lepton number violating versus lepton number conserving modes. And by the measurements of the experiments, one can then put limits on these mixing elements versus the sterile neutrino plane. And the kaon decaying into pion and two same sign charged leptons essentially gives the tightest constraints at the moment. Of course, I mean, the solid lines here correspond to the idealistic limits. One has to keep in mind that the detector size is finite. So one needs to also account for the fact that the sterile neutrino has to decay within the detector. And once one includes such effects, then we essentially drop down to the dashed lines. So in terms of the branching fraction, what it means is that if one only considers the direct limits on the mixing elements, then already some of the modes predict lepton number violating modes well above the current experimental limits. And which is, of course, positive in a sense that it will only get better. One can also think of more than 3-body final state, but of course the kinematics gets more complicated. However, there are some studies which tries to look into this. Now, the question is how robust are these limits? And to check this, something that we did was to look into this scenario where rather than one sterile neutrino, we assume that there are two sterile neutrinos, and that essentially makes the mixing matrix a 5x5 matrix, and it will all the additional mixing elements will contain about 5 Dirac phases and 2 Majorana phases, which can be observed into just one single phase per element, and then one can construct combinations of the relative phases. If one does that, then we find that the lepton number violating modes depend on the combination of the sum of the two relative phases, while the lepton number conserving mode depends on the difference of the two relative phases. And this essentially gives an interference effect, which becomes apparent if we take a ratio of this lepton number violating mode with respect to the lepton number conserving mode. So in the limit that there is one sterile neutrino or there is no lepton number violation, there is only one sterile neutrino, one would expect a flat 1 ratio. However, if one has more than 2, then depending on the phases, one can actually have destructive or constructive interference. And this is also, I mean, some feature that has been observed in terms of collider studies, where people looked, of course, in a much heavier neutrinos. But I mean, the feature is extremely similar. So, I mean, that was for a particular choice of the relative phases. If one now opens up the parameter space in terms of the electron versus muon phase, and we considered kaon decays as an example. So in such a case, one sees that, let's say we take the psi mu equals to psi e direction, then the lepton number violating mode essentially goes through interferences. So one can have constructive and destructive interference on the way, while the lepton number conserving mode will be more or less flat in terms of its behavior. And it can be other way around depending on which direction we choose. So that kind of gives us some kind of a handle on the phases, and one can actually predict, if not exactly, at least some kind of limiting cases based on combining all the lepton flavor and number violating modes. So this has essentially two implications. One is that a negative lepton number violating or lepton number conserving search limit doesn't necessarily mean that the mixing elements are smaller and smaller. It can happen that the phases conspire in such a way that one has more or less number of events in one or the other. The other thing is that not observing lepton number violation doesn't necessarily mean that neutrinos are Dirac. It might happen that we are in a particular combination of phase which is in the destructive interference regime. So what it essentially means is that one needs to be more careful or robust in terms of the constraints that one puts on the sterile neutrino kind of a scenario. Okay, so then
one quick question before
yeah.
moving on. So what is the mass range for your sterile neutrinos there?
So for kaons, of course, it has to be less than roughly the kaon mass. So we assumed roughly 350 mega electron volts.
And it has to be heavier than it would decay then into pion and one of the
exactly
electron or muon. Okay.
I mean, one can do the same exercise for B meson decay, of course, but the problem is the B meson decay limits are rather bad.
Yes, of course. So you have many more kaons.
Here, anything within these two YOLO lines or where the direction that the dashes go is basically ruled out already by the NA62 data. So, I mean, one is already in conflict using realistic parameters because of the interference. I mean, we essentially wanted to have a parameter space which is already directly probable. That's why we kind of chose the kaons.
No, that's good. It's interesting. Those kaons. Yeah, thanks.
Okay, so then this brings me to the last part of my talk, which is about sevens. So sevens stand for coherent elastic neutrino nucleus scattering. The essential idea is that if the energy of the incoming light neutrinos from a reactor is less than roughly the inverse radius of the nucleus, then it cannot see the individual constituents of the nucleus. And therefore it should kind of scatter off the whole nucleus, which gives a nuclear recoil. This is, of course, a standard model allowed process. However, the recoil energy, if one does a back of the envelope calculation, is as small as kilo electron volt. And that's why it took roughly 46 years to detect such a process. And in 2017, basically the coherent experiment reported the first measurement of sevens. The current experiments are already looking at electron volt or tens of electron volt level recoil energy, which is extremely precise. Now, why should we care about the sevens? Because other than doing of course, the standard model precision measurements, it can also be sensitive to exotic BSM scenarios. For example, the neutrino dipole moment. So one of the BSM scenarios that one can right away think of is the active to sterile transition magnetic moment, which is essentially the fact that an active neutrino emits a photon and then goes into a sterile state. In principle, there is also a possibility that the sterile state can go into another sterile state. So these are the two possibilities. And what's interesting is if one has this kind of a dipole moment, that can have a direct correlation with the neutrino mass, which I'll come to in a bit. But I mean, for the moment, focusing on the process where the active neutrino basically scatters off the nucleus and goes into a sterile neutrino. So the sterile neutrino is usually heavier than the active neutrino, and that's why it's often called upscattering. And Primakov was the first one who proposed it. So it's sometimes called Primakov scattering. So such a process would be proportional to the magnetic moment squared. And that essentially means that depending on the number of events that the experiment sees, one can put limits on the magnetic moment. However, of course, I mean, this cannot give us any information about the nature of the neutrinos. But one possibility is to consider that the sterile neutrino, rather than escaping the detector, decays within the detector through another dipole moment. And in such a case, the amplitude will be sensitive to the nature of the sterile neutrino, because again, similar to the meson decays, it will pick up different momentum or mass component depending on whether the sterile mediator is Dirac or Majorana. Of course, it's a three-body final state process, so the phase space is more complicated. But once one gets rid of most of the free parameters, one can basically construct a differential distribution in terms of the outgoing photon energy and the outgoing photon angle with respect to the incoming neutrino beam. And of course, one also has the differential distribution with respect to the recoil energy. So just to motivate why it's useful to have the second sterile neutrino, sorry, the second sterile neutrino, it's mainly because usually the 7s experiments are extremely tiny, in a sense that they're tens of centimeter kind of detector size. Therefore, to demand that the sterile neutrino decays within the detector, one would need a large active to sterile transition moment, which would be in conflict with something like Borexino limits. And therefore, it helps if the sterile neutrino can go into another sterile neutrino, such that the total decay width is can be large. And also because of the fact that sterile to sterile magnetic moments are not so well constrained. I mean, the best limits are from vector mesons decaying into basically invisible states, which essentially proceeds through vector mesons going into a photon and then two neutrinos. Yeah. So just now plotting the differential distribution in the photon energy versus the photon angle plane. So the x-axis is the photon energy and the y-axis is the photon angle with respect to the incoming neutrino beam. What one observes is that for the higher outgoing photon energy, the Dirac distribution kind of falls off quickly. However, the Majorana distribution will be kind of flat. So essentially, I mean, for this plot, we assumed that the neutrino, incoming neutrino is monoenergetic and it's about 3 MeV. So that means the outgoing photon energy minus the recoil energy, which is negligible, can be almost about this 3 MeV. And if at the higher end one finds enough events, then that would imply that it's consistent with the Majorana sterile state. However, of course, I mean, if one really wants to look into a realistic experiment, then rather than having a monoenergetic neutrino, one really has a flux, which one needs to integrate over. And of course, one also needs to take into account the finite detector effects. There are a couple of possibilities, like when the nucleus recoils, it can go into an excited state, and it can even emit like secondary photons and stuff, but such photons would be a fraction of the recoil energy. So one would expect that they're again sub keV or keV order at best. While, I mean, for the sensitivity to Dirac versus Majorana nature, we're mainly interested in MeV kind of energies for the neutrinos, given that most of the reactor neutrino beam energies are roughly few MeV. So to do a realistic case study, we kind of selected a nucleus experiment, which has a working group in TUM. And in the current phase, they basically have a 10-gram detector, and which is about 5 centimeter cube. They also have a possibility to upgrade it to 1 kilogram in future. So that will be roughly 25 centimeters. What is interesting, though, is that they have this outer veto around this detector, which is mainly meant for rejecting kind of additional photons other than the recoil, that can be actually used, according to them, to actually detect high energy photons. Like, I mean, they have a sensitivity of the order of keV when one looks into MeV order energy photons. So that kind of allows exactly the kind of energetic photon that we should produce in our scenario to be detected. So if one now plots, or if one now derives the constraints from the nucleus experiment, so the red is always the 10 gram and then black is always the upgrade. So the solid lines are essentially pure upscattering, where one doesn't have any photon in the final state. But if one has now photon in the final state, there are two possibilities. One possibility is that we don't have sterile to sterile magnetic moment. We only have sterile to active magnetic moment. And the neutrino decays within the detector because of some dark mode, such that the total decay width is of the order of the detector length. So that gives us the small dashed lines. And then if one now also includes the possibility that one has sterile to sterile transition magnetic moment, then of course one can probe to much more lower values for the active to sterile magnetic moment. Okay, so let's assume for the moment that we detect either the Majorana or the Dirac distribution in the differential distributions. So what can it tell us about the active neutrinos? Well, I mean, if we have a Majorana distribution for the sterile states, and then we also have a transition magnetic dipole moment, then kind of like a sector via theorem, one can show that, I mean, one essentially ends up with a light neutrino mass, which is Majorana in nature. Therefore, even though it can be tiny, that would imply that the active neutrinos are actually Majorana. And this can again be a complementary probe to double beta decay or something like lepton over violating meson decays. And of course, depending on the event rate, one can then try to constrain the magnetic moment versus the Majorana mass for the sterile states. On the other hand, if the distribution is consistent with a Dirac case, meaning that in the higher energy, we don't have sufficient events, then one cannot really make any conclusive statement about nature of the light neutrinos. Now, what can it tell us about the neutrino mass mechanism? So the first possibility is that the magnetic moment is essentially generated by some kind of a heavy physics in the loop. And that would essentially mean that that heavy physics will also contribute to the Dirac mass of between the active and the sterile neutrinos. So in a way that if the heavy new physics generates the active, generates the dipole moment, then one has direct correlation between the magnetic active sterile transition magnetic moment and the induced Dirac mass term. And it so happens that the kind of active to sterile transition magnetic moment that you require for the events to be detected at something like nucleus experiment, that would imply that there has to be a huge cancellation either at tree level, or there has to be some kind of a symmetry mechanism to ensure that this kind of mass correction is not large. Okay, I mean, now one can be pessimistic and one can say that we don't want to invoke any heavy new physics and we only believe in type 1 seesaw. Even in such scenarios, one can actually, again, generate neutrino mass using charged leptons. And in that case also, it's the same situation, that if one wants to generate a transition magnetic moment of the order of 10 to the minus 7, for example, one would require a Dirac mass of the order of 100 MeV, which is again needs to be cancelled somehow to match with the tiny number that we get. So essentially what it means is that if we see a Majorana distribution, then clearly the canonical type 1 seesaw type of scenario cannot work. and one needs to have some kind of a symmetry-driven or symmetry-protected neutrino mass mechanism. For example, something like evolution mechanism, which essentially imposes a horizontal symmetry, or something like inverse seesaw. On the other hand, if the distribution is consistent with the Dirac case, then again, I mean, there is mixing between the effective operators. So there are these three independent operators. And even if one starts with zero Dirac mass term, even if one only has the dipole effective interactions, then because of the mixing, one would generate eventually again this mass term. And that kind of again relates the magnetic moment with the Dirac mass term that one would generate. And again, it's very clear that to get something like detection at a nucleus, one would need a Dirac mass rather large, and that needs to be cancelled somehow. Therefore, I mean, clearly, if one would observe any kind of a signature in terms of the radiative mode, that would essentially imply that one has to look into the low scale seesaw with some kind of a symmetry. Okay, so that kind of brings me to my concluding remarks. So currently there are many tensions with respect to standard model, which are hosted by the leptonic sector. And if even one of them is confirmed, that can give us a much needed direction in terms of where to look for or what to think about in BSM physics. High intensity frontiers experiments can really give us valuable hints towards constraining and kind of constructing new physics models, which can explain neutrino masses and can also address some of the standard model shortcomings. In terms of experimental searches, probes complementary to neutrinoless double beta decay can be sensitive to second and third generation of charged leptons. And that's why, I mean, it's important to also look for them. One of them that I discussed is this charged lepton flavor violating and lepton number violating meson decays, which have bright future prospects given the upgrades at LHCb and BEL2 that we expect. And of course, one can also look for exotic possibilities where one can use some kind of a non-standard neutrino interaction to also probe the nature of neutrinos. And of course, I mean, there are many other possibilities that one can explore. And yeah, so yeah, I think that's all I had to say. So yeah. Thanks a lot.
Yeah, thank you very much, Chandan, for an interesting talk. So we have time for questions. Maybe let me start. So you showed there that slide where you showed the sensitivity at the nucleus experiment of just in that last part. But yeah. Can you comment on the other constraints which are in there? Because there are some kind of supernova constraints and so on.
Yes. So the green line is basically xenon 1 ton. And the xenon excess would sit somewhere to the left of the plot that we have. So it's nowhere near where anything is allowed.
Okay.
The coherent, given the number of events that they have observed, so that would be the sky blue region.
So that's just the coherent neutrino nuclear scattering.
Exactly, the coherent experiment. Yeah. So I think they have plans to upgrade, I mean, the next generation of coherent, which would even put stronger limits. And the good part is that coherent is also sensitive to high energy photons. So, I mean, I think they even have a higher energy neutrino source.
Okay, so that coherent limit, does that include the additional photon which is emitted from that?
No. Other than nucleus, everything is standard. Yes.
Yeah.
Then there is limits from BBN and CMB. The CMB is not shown here. So it's basically because of the light neutrinos changing the abundance of the rare elements. And the N2 nu gamma is essentially from plastid, I think. So this is essentially the solar neutrinos coming in, hitting the Earth, and then one would expect that they should decay through a photon. So there are no events, so that kind of constraints that gives us this limit, which is mainly meant for muon type of neutrinos, but one can also convert it to electron through oscillation. Then there is the limit from supernovae, which of course kind of in principle kills, if one really takes the limit seriously, most of the blank space.
So this is one of those classic energy loss arguments, is that right?
Exactly, yes. Yeah.
So you would produce that you produce the sterile neutrinos via the dipole, via the
dipole moment, and then it should cool off. So then, yeah, I mean, that gives you this curve. But then again, I mean, it's kind of maybe a bit debatable that how accurate or how robust the constraint is.
Yeah.
And then all the dashed lines are future experiments. Like if the ship happens, then they will probe this part. So at least, I mean, below this Borexino and BBN, this part is kind of empty, other than the supernova.
Yeah. So for the now just looking at nucleus, so what would you have to do to push up to be sensitive to larger masses for that? What limits it there?
So it essentially boils down to the incoming neutrino beam energy. So if the incoming neutrino beam energy is higher, then one can put higher limits. So that kind of makes, of course, I mean, sevens is not the only possibility, right? One can also have like electron neutrino scattering or something like even at ice cubes, right? Where one has super high energies. True. But the problem is in such cases, it's not a coherent scattering, but one has to then include the form factor dependencies. But it's certainly doable in other experiments as well, up to the form factors. And of course, changing the detector length or the size, it's possible to tune at least the photon mode in terms of that one really probes different masses for the MN also. Yeah. And the decay widths.
Yeah, no, I was just wondering, kind of, if you have higher energy neutrinos, you could push it, or you can probe also the high energy range, and I guess then you can.
Definitely, yeah.
Oh, yeah, okay, good. Yeah, interesting. Other question? I have something about that, actually, the first part of the talk as well. So you mentioned there those LHC constraints on those dimension 7 operators. The scales looked quite low for those, right? That's
these ones?
Yeah. The scales which you broke in.
Yes, I mean, so this is in TeV roughly.
Yeah.
Most of them are actually sub TeV. So some of them are even like not applicable in many cases. But I mean, the most one can go is about 2.5.
Okay,
so,
yeah.
The problem is in at least in dimension 7, if one doesn't have the resonant production, that the event rates are extremely low. So that's why that
suppressed by the operator.
So that's why, because everything is pretty much suppressed by at least once the light neutrino mass, and that's why the event rates are quite low.
Okay, because it would contribute to neutrino mass and.
Exactly. So one actually has to, I mean, once we put, like, I mean, we essentially use MATGraph to do this, right? So we have to code all the different independent operators and see all the possible signatures. But yeah.
It's I can imagine that's always difficult with those higher dimensional operators to get something that really
dimension 9 would probably be even more non-trivial in terms of the number of operators.
Yeah. Oh yeah. I think that will be hopeless, more or less.
Yeah.
Then you have to go to full models.
Yeah.
Okay. So that's interesting.
But I think, I mean,
sorry. Yeah. Go on.
No, so I mean, one of the interesting, of course, I mean, if one has now like this new SMEF or sterile neutrinos, then one can actually get some level of enhancement in terms of LHC as well as the mesons.
Yes. Yeah.
Because then one would suppress the mass or chirality suppression because of the light neutrinos, and there one can get significant number of events.
True. Because you have that additional sterile state. That helps.
But, I mean, then again, I mean, the clash. I mean, this is without imposing the light neutrino mass. So, if one now really takes the light neutrino mass completion seriously, then that would even bring or rule out many of the possibilities.
Mm-hmm.
Which I think is the case in many of the MUE conversions, right? I mean, people get very high rates, but the problem is if one takes into account the light neutrino mass, then I mean, probably many of those scenarios are killed, which can actually predict observable lepton over violating MUE conversion.
True. Yeah, that makes sense, because you would have to amateur tune it also to probably that would work even to tune it. Yeah, that's good. I have one more question for clarification for me. So when you calculated those sterile neutrinos with the meson decays, there is a different behavior for Dirac versus Majorana neutrinos. Yeah, with the propagated here, right? Or maybe just go.
Yeah. Sorry.
Back. Yeah.
Yeah.
Here. Right. Is there a quick argument to see that? And also we need the.
No, it essentially comes from the fact that one has PL, PR in the two vertices in one case, and one will have PL, PL in the other case. So when one has PL, PL, then it will pick up the mass part. And then when we have PL, PR, then one will have the momentum part.
Okay, yeah, no, that makes sense. That makes sense. I was when you went through, I missed that point.
I think I was a bit quick at this part. I probably would have.
No, that's good, and that gives then a different distribution also.
Yes.
Later for sevens.
Yeah. I mean, it's kind of same argument everywhere wherever one has. I mean, the other thing is to really always have this resonant enhancement because of the on-shell thing. Otherwise, the rates are extremely low.
Yes. Yeah. That's right.
But I mean, for single neutrinos, though, I mean, essentially one boils down to the same kind of decay rates. It really becomes relevant when one has more than one, because then one has to really square it, and then one sees the cross terms.
Yeah, those interference terms between us. That's good. Okay. Are there other questions? Everyone is quiet. Otherwise, then let me thank first Chandan for a very nice talk.
Thank you.